Hey guys, what's up? So in this lesson, I'm going to talk about resonance, and I guess I'll give a short definition before getting into an example. So you can think of resonance forms as multiple shades that when you combine give you the entire information about a molecule. So I'm going to use my Professor John Wolf's example that he did in class, which is pretty good. So hopefully you guys are familiar with an aromatic ring. It's a 6-membered ring of carbon with 3 double bonds. And we should remember that carbon double bonds are not only stronger than single bonds, but they're also shorter. Okay? And so if we take that into account, then we should figure that maybe this bond right here is longer than this bond right here, right? Because it's a single bond versus a double bond. However, this is not the case. If we experimentally determine those side lengths, we actually see that all 6 side lengths are the same. So let me write that down. So all 6 sides are actually the same length. And this is interesting because we know that double bonds are shorter than single bonds. So why is this the case? And the answer is that this Lewis structure does not completely represent benzene. And in fact, if we draw any single drawing, we cannot completely represent any molecule. And this is because several electrons found in benzene are not in a fixed position. In fact, they're constantly moving. And so I'm going to draw another picture of our benzene ring. And this time I'm going to label 2 carbons. So this one, and let's say this one. And let me draw in the double bonds. Okay? And so these electrons, the electrons found in the double bonds or the pi bonds aren't fixed. They're constantly moving. And I'm going to draw another example. This is the same exact molecule with the same carbon, same marked carbons. So you see in this one, in the first one, in number 1, there's no double bond between the red carbon and the blue carbon, but in number 2, there is a double bond between the red carbon and the blue carbon, and neither of these Lewis structures individually represent benzene as a whole. But if we take them together, if we put them together, so to speak, then we get the entire structure of benzene, kind of. And this isn't like you overlap them and just put double bonds everywhere. This is you take 50% of number 1 and combine it with 50% of number 2, and you get the complete picture. And this bottom form, actually both forms, are called resonance forms. And a resonance form is the same molecule, only the location of some electrons are different. And we call these mobile electrons delocalized electrons, meaning they are not fixed on a single atom or a single bond. So I'm going to circle these delocalized electrons. So these are the delocalized electrons, the ones found in the pi bonds or the double bonds. So now I'm going to go through my list of rules, or rules of resonance. So number 1 is all resonance forms taken together represent the entire molecule. So all resonance forms taken together represent the entire molecule. Number 2, there are no interconversion between resonance forms. And that means you won't find, if you take a snapshot, I guess, you won't find just, or that's a good way. If you, benzene is not sometimes number 1 or sometimes number 2. It is constantly all of them, which is kind of hard to grasp, but we have to remember that electron movement is extremely fast, and this molecule is constantly changing form. So if you take, like, if you look at the ceiling fan while it's going, you don't see the position of each fan blade. You see a disc, and that's because the fans are moving really fast, and you see everything. So, and that's why there's no interconversion. It's all of them at the same time. Number 3, resonance forms are not different molecules. They're different depictions of the same molecule. And then my last one is that resonance forms have different weights or different significance. And I will get into that a little later. So resonance forms have different weights. Meaning that one resonance form may better represent the molecule than another, and this is based on stability. And I guess I'll show you an example. So clear some space. So if you remember from the first video, I drew this guy. And then I said, this is when we were discussing formal charge. And then I drew another molecule, except I lied to you. It wasn't another molecule. It was actually the same molecule, just a different resonance form. That's a minus sign, sorry. So yeah, these two are actually the same same molecule, just different resonance forms. And the arrow in between them, the double-sided arrow, means that they are resonance forms. There's not like a reaction going on. They're just resonance. So this is a good example to use about the rule number 4, which is the different weights. So which one do you think is more stable? And if you said the one on the left, you would be correct. And this is because it has fewer number of formal charges. In fact, it doesn't have any formal charges, and that makes it more stable. So lacking formal charge means it's more stable, and because it's more stable, this structure has more significance when representing the molecule because it has more of this form as its characteristics. You could kind of break it up into percentages and say, okay, this represents 90% of the molecule, while this represents, let's say, 10%, and those numbers are made up. But yeah, we can and why this is important is that we can evaluate the significance of different resonance forms relative to one another, and there are rules for that too. So I'm just gonna list them in order of importance. So the first one is open shell versus closed shell. Oops. Closed shell. The second one is formal charges, and this is in order of importance. So the first thing you should look at is open shell versus closed shell. in resonance forms. And then the third one is electronegativity. And I'm just gonna leave that for now. I think this is a good place to stop. I will get into what this actually means in the next section, and I know I haven't really explained on how you can see resonance in a molecule, or how you can draw resonance forms given the structure of a molecule, but I will get into that later. Since I've already gotten into this, I think I'll just finish up on how to relate the significance of different resonance forms, and then we'll go into drawing resonance forms. So thank you for listening. I hope this cleared up resonance for you, and I'll see you next time.